Two water utilities. One reports 20% water loss, the other reports 5%. Most people would say the second utility is 4 times more efficient. Most people would be wrong. Today we are going to show you, with the real numbers, why the most common water loss metric in the industry is hiding a scandal. Here is the setup. Utility A and Utility B have the exact same network. 100 kilometers of mains, 5,000 service connections, 45 meters of average pressure, and both of them are physically losing the same volume of water to leaks every single day. 800 cubic meters. Same cracks, same joints, same failing infrastructure. The only thing that is different is who they sell water to. Utility A serves a quiet residential neighborhood. Its customers consume 3,000 cubic meters a day. Utility B serves a zone with a large industrial customer, a factory, a data center, anything thirsty. Its customers consume 15,000 cubic meters a day. Now we report water loss as a percentage of total input. Utility A's 800 cubic meters of leakage is 21% of its input. Utility B's identical 800 cubic meters is only 5%. One gets a headline saying inefficient, the other gets an award for conservation. Same broken pipes, different story told. To see why percentages lie, you have to understand the standard water balance. This is the framework the International Water Association and the American Water Works Association use to audit every drop. Every liter of water entering the system ends up in one of 4 places. Revenue water, the water you bill and collect for. Unbilled authorized use, firefighting, hydrant flushing, legitimate uses you do not charge for. Apparent losses, meter errors, theft, billing mistakes. And real losses, the physical water that escapes from your pipes before it ever reaches a customer. Real losses are the ones that hurt. They represent treated water, pumped with real energy that leaks back into the ground. And unlike metering errors, real losses respond directly to the hydraulic state of your network. More pressure means more leakage. Lower pressure means less. That makes real losses a physics problem, not an accounting problem. Here's the problem. The percentage of input metric divides real losses by total system input. The numerator, the actual leak, is a function of your infrastructure. The denominator, the input volume, is a function of your customers. And those two things have nothing to do with each other. So if a big industrial customer moves into your service area, your leakage percentage drops overnight. You did not fix a single pipe. You did not lower a single meter of pressure. You just diluted the number by adding more consumption to the bottom of the fraction. The metric rewards you for selling more water, not for leaking less. That is why 2 utilities with identical failures can look 4 times apart on paper. The fix is to stop measuring against the customer and start measuring against the infrastructure. The International Water Association proposed a benchmark called Unavoidable Annual Real Losses, or UARL. It estimates the minimum volume of leakage that a perfectly managed system with this exact infrastructure, this length of mains, this number of connections, this operating pressure, would still physically produce. It is a par score for leakage. Divide your actual real losses by the UARL and you get the Infrastructure Leakage Index ILI. For both of our utilities, the UARL is 263 cubic meters per day. Both of them leak 800. Both get an ILI of 3.04. Category B, same performance, same infrastructure reality, no trick. So if ILI is so much fairer, why is it still not the universal default? The honest answer is not that the math is hard. 3 things get in the way. Most utilities do not have the calibrated metering and night flow analysis needed to calculate real losses accurately. Regulators still ask for percentages, so that is what gets reported. And the UARL formula itself has limits. It overpredicts in small systems with fewer than 3,000 connections and breaks down below 40 meters of pressure. Outside those bounds, your benchmark lies back to you. In the next episode, we build UARL from scratch. Where do the coefficients 18, 0.8, and 25 actually come from? When does the formula break? And how do you apply the system correction factor so the number stays honest? If you run a water distribution network and you want your performance metrics to stop lying about your infrastructure, subscribe to Transparent Blue Water and stay with the series.